In this video, we will discuss the IV characteristics of diodes. At first, we should keep these 2 points in mind. The diodes are nonlinear passive devices. They are nonlinear because their IV graph is not straight, and they are passive because they cannot be controlled. In the previous video, I had mentioned that diodes are uncontrollable switches. So they are switches, but they cannot be controlled, and that is why they are a passive component. And we will learn why their IV graph is not straight. Why is it non-linear? But first, we will start with an ideal diode. The IV characteristic of an ideal diode will look something like this. This line here is, this part is the forward bias, and this is the reverse bias. The y-axis is current and the x-axis is voltage. Now observe this graph and try to understand what it means. What this means is, in forward bias, the diode conducts perfectly. So diode is short circuit. So it perfectly conducts and allows current to flow without any resistance, without any losses. But in reverse bias, there is zero current flow. It's touching the x-axis. So there is zero current flow, but there is maximum voltage drop. So all the voltage is dropping, nothing is flowing through. So in reverse bias, diode is open circuit. Now this is the case for an ideal diode. Ideal diode in an imaginary world. This is not possible. This is not possible in the real world. Now why is it impossible? Because there are some variables and some losses which we will get to one by one. The first thing we'll consider is barrier potential. Barrier potential. This is the minimum voltage that must be applied across a diode in forward bias for current to flow. Okay? Minimum voltage required for current flow in forward bias. Now if we draw a graph, it's gonna be a bit different from the last one. So this side will be the same, but now we have a barrier potential, so current will not flow until a certain voltage is reached. Usually it's, for silicon diodes, is 0.7 volts, something around that. It will be a small voltage, but let's say here is our 0.7. So until here, until this point, there will be no current flow, and then from here we have ideal conditions again. Okay, so this part is our barrier potential, and we can represent it as VD or VK. And for silicon diodes, is usually 0.7 volts. Each diode has its own barrier potential. It depends on diode to diode. So again, this is forward bias, and we can see that after the barrier potential is reached, current flows. So diode is short circuit. Current flows perfectly, ideally. And this is reverse bias, where there is zero current flow, ideally again. Now let's introduce another variable, another part of a real diode. Now we will introduce resistance. Remember, diodes are physical components, and all physical components that conduct electricity will have some sort of resistance unless they are superconductors. So even though we say that diodes in forward bias are short circuit, in reality, practically, they have some resistance. It is very minor, but it is still there, and that makes the IV characteristic slightly different. IV graph. So again, we have the zero voltage, zero current here, and remember barrier potential. Okay, so let's say we have it until here. This is the barrier potential, VD. After this, what's gonna happen is, instead of going straight up like it had before, it's gonna go slightly like this. Okay, now why? Because there is a resistance. When current starts flowing, there will be resistance within the diode. We know I equals V over R, so V equals IR. Now when the diode is it's closed, so basically that is turned on and it's allowing current to flow. As current is flowing and there is a resistance, the voltage will increase, the voltage drop. So as current is increasing, voltage drop will also increase. That's why instead of going straight up like this, it's slanted. And again, this is forward bias and this is reverse bias, where it's open circuit almost. Now we will take one last thing into consideration, which is breakdown voltage. Breakdown voltage. Now, although we say that current doesn't flow in reverse bias through the diode, if enough voltage is applied, the diode will break down. So if enough voltage is applied, all insulators break down. And the voltage at which they break down is called the breakdown voltage. Now each diode has a breakdown voltage in the reverse bias. This varies from diode to diode, depends on each diode and the manufacturer. Now if we draw a graph by taking the breakdown voltage into consideration, we will have again something like this here, and then we will have the diode voltage, VD, the barrier potential, and then we will have the current. I shouldn't look at that. Yes, okay. Here we have VD, here we have current and forward bias, but here we will have, at a certain point, after that it'll just drop like this. Okay, it'll be mostly linear, so almost straight, but not exactly. And also here it will be slightly dropped here, because there is some reverse current, but very small. It's so small that it can be ignored. So we can just draw it like that by ignoring it, but there is something. It's not exactly zero, it's in the nanoamperes. Now this point, this is the breakdown voltage. So let's say VBD is breakdown voltage. And what happens after breakdown voltage? After the breakdown voltage is crossed in the reverse bias, and of course this is a reverse bias. Before the breakdown voltage, there is almost zero reverse current, but after breakdown voltage, it becomes another short circuit. So reverse current increases rapidly, and this is called avalanche current. Avalanche current. because like an avalanche, the current just goes through very fast. So this is our final IV graph of a real diode, by taking into account real operating losses and manufacturing defects and everything. And yeah, and due to manufacturing defect, because manufacturing cannot be perfect, each diode will have its own breakdown voltage. Some will be here, some will be a bit more extended like this. Yeah, that depends on each diode. Same with the breakdown voltage.